someone might have worked on image processing techniques, someone might have worked on control techniques, path planning algorithms, and so on. So I'm sure there would be various courses in your next upcoming year, third year, final year, and I would recommend you to take these courses so that your level of knowledge also increases, and you will eventually be able to apply these into real world problems. Moreover, of course, we'll have presentations now, but if you have really solved the problems, especially those which were selected from this MathWorks Excellence in Innovation program, if you have successfully solved those problems, I would recommend everyone to submit their solutions onto the web page that we had already shared. I will also reshare that with the organizers if required. Uh, and if your solution gets selected and if it is accurately solved, then you might also get certificate of merit from MathWorks as well. So this is something that I would recommend. If you have already solved the complete problem, you can right away submit your solution. If not, you can still work on that particular problem maybe next couple of months, and then you can submit on that particular page. Moreover, since you're from IVDC and Robotics Club, I would recommend you, since you have solved these particular problems in your own way, and if you think these are, the novel solutions that you have provided, I would also recommend you to maybe participate in one of the conferences that has robotics or autonomous vehicles as a theme and present your work there as well. That will also sort of help you to uh, promote your work that you have done, and eventually that will also add into your resume and CV while you're participating or while you're applying for your post graduations and so on. So yeah, I'm I'm pretty excited to see what you have done. And yeah, over to the organizers, and we'll go through the presentations maybe now, and let's see uh, what do we have here. Thanks.
Thank you, sir. And as a mentor, I also have to say that they have learned a lot through these projects. Out of four projects, I believe two of them have been chosen from the MathWorks Innovation Excellence and Innovation projects. So,
Okay.
with that, I guess we should start with the first group, IVR1. Yeah. So, I'll just hand it over to them.
Good evening, esteemed judge, and everyone present here. I am Bhavna Chaudhary, and I am delighted to have this opportunity to present our work on the project to develop a robust lane detection pipeline using limited computation power. In a world which is increasingly reliant on autonomous vehicles and advanced driver assistance systems, safety and accuracy is more critical than ever before. Our project focuses on addressing the challenge of lane detection with a specific emphasis on accuracy, efficiency, and limited computation power. I am truly excited to share our journey on our project. I would like I would like to introduce you with my team. I am Bhavna Chaudhary and my team members are Arjun S. Nair and Ambadi BR. We were constantly mentored by our mentors Sairaj Loke and Kshitij Bhatt throughout our journey. So, this is the tech stack which was used in our project. As you can see, there are various frameworks which we use like TensorFlow, PyTorch. We used IDE such as Jupyter Notebook. Now, I would like to hand over the stage to Arjun to take you on a tour of our workflow.
Okay, so I'll be briefly telling about the workflow and a general overview of our project. So initially, we divided our project into two approaches, mainly approach one and approach two. Approach one was focused on computer vision techniques. For this, we took references from various open source resources such as the PySource lane detection using OpenCV tutorials, as well as we took up a course on Kaggle on computer vision, lane detection using computer vision. After the successful development of a pipeline that could detect lanes from images and videos, we evaluated them. But we found various problems with this computer vision based pipeline. Then we shifted our approach to CNN based models, that is mainly using deep learning techniques. So we found two CNN models from online repositories, and one of them we chose and trained on a custom dataset. We have provided the link of the dataset in our repository, and finally we ended up with three CNN models. Each of us we worked on each CNN model, and finally we were able to get a common pipeline that would take the pre-trained CNN model as input as well as an input video, and would result an output video with lane predicted. So after the successful implementation of the CNN models, we evaluated them using various metrics. We tabulated them and even plotted them. And afterwards, we shifted our focus to already existing panoptic segmentation model such as YOLO-P, YOLO-PV2, and hybrid nets. The main agenda behind choosing these three were that they were trained on the common dataset, the BDD 100K dataset. Furthermore, we worked on them and we obtained robust results using them. As you can see in the background, this is the result that we obtained on YOLO PV2 model. And this is an inference video we took from our campus. And after the successful implementation, evaluation, and plotting everything, we shifted our approach to a recently developed concept in deep learning called as transformers. We used a transformer-based lane detection model to detect lanes in our inference video. Further, in the future scope of our project, we have added quantization, in which we'd be choosing one model. We have here chosen YOLO-P model, and we'd be quantizing it so that we can deploy it on edge computation devices like NVIDIA Jetson Xavier NX. Now I invite Ambadi to brief about approach one.
So going on to approach one, in this method we use traditional method to detect the lanes. The images are passed through different sequence of process to detect the lanes. In pre-processing, we converted the RGB images to grayscale. Then we used Gaussian blur to enhance the image. For this, the kernel size parameter is used to define the blurring of process. And in canyon detection, the edges of the images are detected. This has mainly two parameters: maximum threshold as well as minimum threshold. This defines the sensitivity of the detection, and also region of interest. In this, most images we have skies and other parts which are not important. So uh, to choose the most important parts, we use a quadrilateral using a region of interest. Then probabilistic Hot transform to draw the lanes. The detected images are passed through probabilistic Hot transform to detect the lanes. In post-processing, we added the lane detected images with the original image to get the final output. Going on to disadvantages. Yeah. As we can see in this video, initially it is not detecting the curves, but as we go, it detects perfectly. And in final part, due to saturation, it is not detecting the lanes again. So this non-dual model fails in detecting at complicated curves as well as highly unsaturated roads. Also, it fails in foggy and rainy conditions. Next, I invite Bhavana for approach 2.
So, to overcome the challenges discussed and to boost the limits of our lane detection pipeline, we took the approach of deep learning methods, in which we started with three basic CNN models. And in the start, it was useful for us, but soon we encountered some limitations, like only single lane detection, not drivable area detection. Also, in bad weather conditions like very foggy and rainy conditions, our CNN models were not able to detect proper results and they were not accurate. So we searched for some good models which can give us very high accuracy and FPS. Our search led us to some panoptic segmentation models like YOLO-P, YOLO-PV2, and hybrid nets. We tried 3 of the models we evaluated, and we found the best model among this. After that, we also thought to explore much, and we then tried our LSTR model. All these will be discussed in detail. So this is the data set. We used BDD 100K dataset for 3 of the models. This custom dataset, which you can see, we took images from our campus roads, and also these are the some lanes drawn on the grass. We took this because we took this in further thinking to collaborate with IVDC club of our campus, so that we can contribute to the IGVC competition, namely Intelligent Ground Vehicle competition. We thought of fine-tuning the models on this dataset. So this is the basic model architecture of YOLOP. The brief about this: it contains backbone, neck, and then detection heads. What it does is, we get the input image, which is a RGB image. We feed this into this backbone. This backbone extracts the features, and these feature maps are passed through the neck, which refines these feature maps. After these refined feature maps, the detection heads detect the lanes, drivable area, and object detection. By the way, object detection was not the primary focus, so we focused only on the lane detection and the drivable detection. This is the architecture of hybrid nets. More or like the architecture is similar, just the differences in the backbone. Here we used efficient net B3, and in YOLOP we used CSP darknet. And here in neck by FPN module is used, whereas in YOLOP only FPN module is used. By FPN is the extended version of FPN module.
Okay, as Bhavna discussed before, LSTR model architecture is also similar. It basically consists of this backbone, neck, and the decoder part. One main difference is that it has an additional part called reduced transformer network. This is the core of the transformer network that we are using. Basically, it is based on this self-attention mechanism. This allows each element in a sequence to attend to all other elements in the same sequence. Like if you take an example, if you take a feature vectors in an image, each feature vector can attend to all other feature vectors in the same image. Like if you are computing the weighted sum value of other elements, this weighted sum value of other elements can be based on the single element. So this significantly increases the computation power by reducing the inference time. And in LSTR model, the activation function used is the softmax activation function, and the error loss function used is the cross entropy loss function. Now, this is a slide that shows the evaluation of the first 3 CNN models that we used. As you can see, we evaluated the parameters, size, FPS, and in addition to all that, we found various other metrics such as precision, recall, dice coefficient, intersection over union, and F1 score. We thoroughly evaluated these 3 CNN models based on all these parameters given. We have tabulated them, as you can see, and then we have plotted them using matplotlib library. As you can see, in terms of parameters, in terms of precision, CNN model exceeds all the other two. CNN model 1 exceeds the other two models. But in terms of FPS, CNN model 3 exceeds both the other models. But one of the very good parameters is intersection over union, in which CNN model 1 exceeds the 2. Thus, we can conclude that CNN 1 was the most robust among the 3 CNN models. This is a GIF file that shows the comparison between these 3 CNN models. Now, moving on, we then evaluated the panoptic segmentation models also. Similarly, we computed the parameters, size, accuracy, FPS, and other metrics. And in the graph, you can see YOLOPV2 leads in accuracy as well as FPS, while in intersection over union, HybridNet leads over YOLOPV2. And this is a GIF file that shows the inference that we obtained. As you can see, the first GIF file is on a standard highway. We can easily compare between the 3 panoptic segmentation models. But to push this to the limit, we ran this on a campus video that we took in our own campus. And as you can see, you can much more efficiently compare between the 3 models here. YOLOPV2 seems to be the most efficient, followed by HybridNets and YOLOP. Now, moving on to the future implementation of our project. So, the future implementation of our project is to deploy our model on edge computation devices, namely NVIDIA Jetson Xavier NX. So this is a very powerful device consisting of a powerful 64-bit processor and an 8 GB RAM. But even though the processor is CPU processor is very powerful, when we run complex lane detection models, it fails as compared to its GPU counterpart. So the need for quantization was high. So initially we had to choose a model. So the YOLO PV2 and HybridNet, both these models are built upon the YOLO P architecture. Thus, we chose YOLO P architecture, and it had comparably less parameters compared to the other two. So this quantization file we built, it is built on top of the PyTorch Python library. We applied static quantization by reducing the FP32 pixel values into int8 values, and thus we intend to quantize the model. Okay.
In this project, we have mainly used three systems: two HP Pavilion gaming laptop with a Ryzen 5 and 8 GB RAM, and another with a Ryzen 7 and 16 GB RAM, and an Asus VivoBook 15 Pro with Ryzen 5 and 16 GB RAM. In our future work, we will also be implementing neural network pruning. Improving increases the model accuracy as well as decreases power consumption and inference time. So for pruning, we will be first analyzing the model and removing the least important parameters from the model, and this decreases the size. Then we will be fine tuning the model again to get the accuracy back due to pruning, that is lost due to pruning. This we will repeat this process so that we can reduce the size as much as possible and increase the and decrease the size, and also this decreases the power consumption to minimum.
Okay, as I have mentioned before, the future improvements of our project is mainly to deploy our model on NVIDIA Jetson Saver NX. But the thing is, like, even though it has an 8 GB RAM, ideally 2 to 4 GB RAM usage would be a practical upper limit. So the CNN models that we tried first, they could be easily deployed on this device, but the YOLOP model, it had to be quantized. So that is why the need for quantization was here. And these are the references that we have used in our project.
By presenting our work today, we are very happy and we hope to inspire future research and development in the field of lane detection and to foster a future where autonomous driving is very safe and reliant. We look forward to share progress in our future. Thank you.
Sir, if you have any questions, you can ask them now.
Sure, yeah. Thank you. Thanks, team, for presenting your great work. Uh, I mean, it's very nice, and the results that I see are also quite encouraging. That you're able to successfully detect the lens and using various different kinds of models. So that's good to know. Just few questions. So you said you developed three CNN models. So were they developed from scratch, or did you use it from some repository or something?
No,
How was it?
we found two CNN pre-trained models from online repositories, and we
Okay.
took one of that and we trained it on a data set that we found online. The third one is the trained one, and that is the for better one. Means the CNN model one is the trained one.
Okay. And that's, I mean, so in that model, you just took a different data set, or did you also change the layers of that CNN model?
No, we didn't change the layer structure, but the two CNN models, they differed in layer structure. Means in the
Okay.
number
Yeah.
of convolutional layer structures.
Right. Yeah, sure. No, because why I asked is, since you said, I mean, CNN models can be easily deployed onto edge platforms. If you tend to improve the accuracy of these CNN models, if you maybe work a bit on improving the architecture of the CNN in itself, that might also improve your results, and then CNN deployment onto the edge devices could also be little easier, right? So, I mean, I'm sure you might be aware there is a technique called transfer learning, right? So you can take a pre-trained model, just modify the architecture a little bit of that pre-trained model, and then you can train it on your particular data set. So that will be customized and also customized for your application, and it may provide you the better results as well.
Yes,
Uh,
sir. Yes,
I
sir.
mean, that's one thought. Other thing, you also mentioned it was not giving proper results into rainy or foggy conditions, or I mean, different weather conditions in some cases. So there is also a technique called as data augmentation. I'm sure again you might be already aware of that. So
Yes.
whatever images or whatever videos we have, right? So we can use data augmentation technique to add these various varieties of weather conditions and all that, so that you can retrain your model onto these conditions as well. And then if you probably train these models, all of these models, not necessarily only CNN, other models might also give you better accuracy in that particular case, right? So, I mean, yeah, more than questions, these are just comments from my end. Yeah, question is like, so one question. So, did you use any? So, for example, in the road that is there in the backdrop of the slide, we see there are lane marks which are there in white color. So did you happen to use these lane marks as one of the features or something like that, or how are your models working in this case? So, for
Yes, sir.
example, if the road does not have lane marks, what whether it will still be able to detect the proper lane?
Yes, sir. These white lanes were used as a features, but the YOLO PV2, they were trained on the data set, and the augmentation technique was also used, in which some images were there where lanes were not there. So it was able to perform good on those images as well.
Okay, so what is? I mean, of course, these are deep learning models, so we'll not be able to understand what's happening deep inside. But what do you think uh, is the technique that is being used to detect these lanes without having lane marks? What is? Do you have any idea about that?
It's like finding the right and left lane and like computing the center point and like detecting the drivable area.
Hmm. Okay,
We
yeah,
had
that
gone
could
through
be
the architecture of the model. It was we inferred such.
right. Sure, sure. Fine. And you mentioned about LSTR model. I mean, so you use CNN, YOLO PV, and then LSTR. So what exactly was the improvement in LSTR, and do you find any limitation in using that model?
Yes, sir. There was limitation in robustness. Like we could show the slide. Like as you can see here, this was the prediction made by LSTR. Uh, like this is the inference video that we run on our campus. The lanes
Uh-huh.
are getting predicted, but like they are not as efficient as the YOLO PV2 or YOLO P model architect like models.
Right. But then what is the advantage of
It
using
has a very
LSTR?
significantly high FPS. Like compared to YOLO PV2, it has like an FPS increase of 10 to 20. Like YOLO P we ran on our like device CPU. It gave an FPS of 49, but this gave a FPS around 60 plus average.
Okay, okay, sure, yeah. So I think there can be still little bit of improvement that can be done on LSTR model then,
Yes, sir.
so
That's
that
included
which
in
can
our future
also
works.
right, so that which can also help you to get a higher FPS with more robustness as well. Sure, fine. Yeah, that's thanks for presenting and all the good work. Again, I'll just recommend one thing. Since you have used multiple of these models, I'll recommend you to just also go into theoretical aspects of each of the layer, what each layer does in each of the architecture and so on, and why does that particular architecture works better. I mean, of course, now you know which architecture works better in this case, but you should also be able to understand like why it is uh, better architecture than the other one, right? So just maybe you can take any of the course or try to learn by yourself and so on. But yeah, overall, nice work. Thank you.
Thank you, sir.
Thank you, sir. Those were some excellent insights. How is the event so far? Any audio issues? Any visibility? Maybe anything from our end?
No, I mean I'm okay. I can see the presentation and I can hear you quite well. Yeah,
Great, sir.
that's
I'll call upon IVR two, which is okay. You guys can introduce yourself, right? So, basic introduction. What are you doing?
So hello, sir. We are the IVR2 and we are working on the autonomous navigation in a rough terrain. We have to move. Okay.
We're just opening a presentation.
So We are the BTech third year mechanical students. I'm Aditya Swalka. My colleague Abhishek and I will start the presentation.
Just one moment, I'm opening the presentation. Sir, am I audible?
Yes, I can hear you.
Okay. Okay, so good evening to everyone. I am Abhishek Nair, and I, along with my teammates Aditya Savalka and Tejal Uplenchwar, will be giving you a brief insight into our project Autonomous Navigation in Rough Terrain. This is a MATLAB Excellence in Innovation project. And okay, so what we had to do is that we had to create a navigation system for a bot traversing in a rough terrain. It involved mapping the environment, path planning, and avoiding obstacles. We used a co-simulation of both ROS and MATLAB for the complete project and to make the bot completely autonomous. These are the tech stacks used, main focus being on MATLAB and Simulink toolboxes. So, to give a brief idea into our roadmap, so as every other PS, we started off with understanding what exactly we had to do. And in our PS, the first task we had to do was understanding which robot to take and which terrain to go through. So we started off with three bots: Turtlebot, Curiosity Master Rover, and Cleopatra Jackal. The first bot we tested with was the Turtlebot, considering that it had a lot of documentation. But we realized on the way that Turtlebot is not a very good bot for rough terrain navigation. So we switched to Curiosity Master Rover, and once we understood how the motion works, we switched the sensors of these Curiosity Mars rovers. There was some issue with the configuration of the sensors. We tried restoring them, but we faced some difficulties there, which is why we quickly switched to Cleopatra Jackal, and that was the main basis of our project. And we'll be explaining in depth about each and every part, like the ROS section, the MATLAB section, and the sensor data visualization.
So now I'm going to tell you about the various sensors which we use, because if we just employ one sensor and use the one bot in the only one environment, that it will become difficult to judge whether the sensors are good to map a certain environment. So these are the various sensors which we implemented on the Jackal. You have to play with the URDF files and the parent link, chassis links, all those things, and then after that you can able to implement these sensors. Certain sensors like Velodyne, Hokoyo, Real to Sense cameras we implemented to make the 3D map of an environment, and the uh, SI6 LMS11 like 2D laser scanners, point gray cameras we use for the 2D mapping of environment, as all project is based on the 2D mapping and navigation. Now I'll move to the Curiosity Mars rover. There are the certain cameras we have to download certain packages as well, so we can correct our misconfigured sensors. So I'll like to show you our simulation of the Mars rover. So you can see that uh, using the cameras, using the laser scanners, our bot is seeing the environment. Its map is already preloaded in the MATLAB system, and that MATLAB system is Simulink model is providing the waypoints of the shortest paths in which our robot has to go. And in the gazebo ROS, you can see that it is doing the obstacle avoidance and trying to find the shortest path which is possible.
So the first part that we covered in ROS was mapping the environment, and as we know, mapping can be broken down into these parts, and which is basically data acquisition is basically getting the data from the sensors, then calibrating the sensors. Pre-processing the data involves removing noise and some other outliers in the data. Feature extraction is the main part where we basically extract certain lines and other landmarks in the environment so that the bot can start mapping the environment. There was some map optimization and visualization also used. There are different mapping algorithms that we went through, and some of them are G mapping, Hector Slam, RTAP map, Cartoslam and Cartographer. We chose Gmapping because it is the simplest and the most efficient one to apply in places where the computation power is less. So our Gmapping is basically a FastLam, grid-based FastLam method, and I would say that each and every mapping algorithm has its own pros and cons. It depends on what kind of environment we are mapping and what kind of processing power our bot has. So we have to weigh our pros and cons to choose the right one, and we went with Gmapping. So now moving on to the MathWorks part where we used MATLAB and Simulink software.
So, coming to the part that we, oh, I cannot see this. Oh, wait. No, hello. So, coming to the part that we did using MATLAB. So, path planning. So, what is path planning? Basically, it is the task of finding a path from the our start goal to from start to goal. So, what our path planning algorithm does is give our robot waypoints to follow. So, all the algorithms that we implemented are graph based. For that, it works by discretizing the map. That's why we used occupancy map. This is the office world that we used. This is the map that we used, and in this map we implemented all our algorithms. So the first one is A star algorithm, search based algorithm. So giving the overview of this discretizes the state space into grids. Each grid is allotted one cost. The And it works on the basis of cost function by minimizing the cost function. So the cost function is the addition of the g cost and h cost. H cost is heuristic cost and g cost is the actual cost, which is from the start node to the current node, and the heuristic cost is from the goal node to the current node. And by minimizing this, A star algorithm is able to find the shortest path. A star is efficient. A star always finds the efficient path, but there are some limitation of A star. We cannot go into more dimensions because the computation complexity increases. So this is the implementation of A star in our office map. Next up, we have RRT. So it is a sampling based algorithm. So in a state space, it just samples random nodes, and for that node, for that parent node, the more nodes are sampled, and until and unless the goal is reached. RRT may not give you the shortest path, but it will give you the path very quickly, which is feasible. Uh, Moving on, this is the implementation of RRT in our office map. So this is the implementation of RRT star. So basically, RRT star is the extension of RRT. Here, rewiring of nodes is also allowed. So over the time, over the when we increase the iterations, we can get an optimal path, which is the shortest. This is the hybrid A star. It is same as the A star algorithm. In A star, the map is discretized into grids. So here also the map is discretized into grids, but it has the approach of RRT star. It has a RRT approach. Like it sees the environment as continuous rather than discrete. So it actually brings the algorithm closer to real life, because the space in real life is not discrete, it is continuous. So it visualizes the space as continuous and gives more better results, and it of course gives the shortest path. So in summary, RRT star is of course the improved version of RRT, but based on our application, if our map is not so complicated, we can use RRT. RRT stars is optimal, but it comes with computational complexity. Uh, and comparing A star and hybrid A star is closer to the real world. And that's all from my side.
So once we get the waypoints of the world, we have to work on the motion planning. But before that, the bot needs to localize itself. It needs to know that where exactly it is located. So we, for localization, we went with adaptive Monte Carlo localization, and for that we use the principle of Bayes theorem. And what it basically does is that in this localization, it, instead of using an extended Kalman filter, it uses a particle filter where a lot of particles are deployed in the map, and they are given certain weights. Weights are basically probabilities, and as the bot moves, these weights are updated, and every time a point with a higher weight is chosen and a point with a lower weight is discarded. The AMCL is able to dynamically adjust the number of particles. It depends on basically how complex the environment is. So this allows us to save computational resources. If it's a more complex environment, it will be computationally heavy, but if it's a simpler one, it will be computationally lesser heavy. But before going into localization, what we do is that we need to load the transformations. So transformations are basically the spatial relations between various coordinate frames in a 3D area. So they're in ROS, they're stored in this data structure called TF tree. What basically it is that there are certain nodes in a TF tree. These nodes represent the various coordinate frames, and the line joining these nodes are the transformation. So why it is necessary is because the frame, let's say a bot has a base frame and there is a frame in the camera. The base frame is different from the camera frame. So there should be some relation between these two to ensure that the data received from the camera is properly. Just one second, sir. Is the screen still visible, sir?
Yes, I can see the localization slide.
Okay, okay. Thank you, sir. So the transformations are thus necessary because it helps us to properly localize the bot. This is an example of the localization script we ran on MATLAB. So once the bot is localized, the transformations are loaded and the waypoints are given, we can move on into the motion planning of the bot. So the motion planning Simulink model is consists of four submodels and one main model. We'll be through them one by one. So the input model basically has it basically takes the input from the user. So when we do a co-simulation between ROS and MATLAB, we are able to access to the topics in ROS. So the top block gives us the laser scan messages, and the second one gives us the ODOM messages, and at the bottom we can load our waypoint. So what happens is that this is a very versatile model because the laser scan topic and the ODOM topic can be changed according to the bot. Every bot uses a different topic to get these data. So once the data is received, then we move on into, we use the pure pursuit controller, and what it basically does is that it recognizes the target point and then it aligns the bot to that target point, and then it provides velocity so that the bot can reach that particular point. That's where the pure pursuit controller comes into play. After that, we also the model also has obstacle avoidance properties. So let's say there is an obstacle that comes in between the bot and the target point. The bot realigns itself to the closest alternate path that it can take, and it continues the same process of pure pursuit controller. So the output block, what it does is that it takes all this data that we have given it, and then it uses the velocity publisher of the bot, and it supplies the translational and rotational velocities to the bot. And our bot used CMD well topic. Almost all the bots we have used, the three bots we have used, use the CMD well topic for publishing the velocity messages. But it can be changed based on what the bot is. So this is the main model where all the data is compiled and the messages are received from ROS, and the messages are published into the ROS system. So now moving on into the 3D mapping.
So now I'm going to tell you about the advanced section of our the problem statement, which is the 3D mapping. So the basic 3D mapping frameworks, which you can see everywhere in every robotic applications, are the point clouds, elevation maps, and the surface level maps. But there are certain limitations of these maps. You can see there is very important for a robot to differentiate between an unmapped area and a mapped area so that it can navigate in the free space which is being differentiated by a robot. Second, there is always an uncertainty, like all these maps run on the uncertainty. What I meant by uncertainty is that what is the measuring distance of the obstacles from the sensors. So our main task is to reduce that uncertainty and correct our map. So how can we reduce that uncertainty? We can implement lot of sensors and combine the lot of sensors data to reduce that uncertainty. Third important limitation is that these maps requires a lot of memory usage. So we come with a new technology, which is the Octomap, which is implemented for the ROS 2, ROS Humble, ROS Foxy. So we changes a lot of packages to use that in the ROS 1, and it allows us to handle different sensor noise and try to merge all the different sensors data to create a map. It is efficient, it compact in memory and on disk. It provides a collision free. It provides us a differentiation between a mapped and a unmapped area. So why it is that much efficient? Because it worked on the 3D data structure, I can say the octree. Octree is basically divided into the each octree is divided into the 8 columns, I can say. And that column we can also say it as a node, and each node is known as a vowel. In each vowel, there is a clear representation, like which area is the mapped area, whether in that area is the obstacle is that. Here you can find our simulation of the 3D map. We stored this 3D map in the occupancy.bit file, and you can visualize that bit file with a lot of softwares. Next mapping technique which we use for the 3D mapping is RTAB, real-time appearance-based mapping. What happens in every mapping technology, they works on the three things. First, landmark-based constraints, odometry constraints, and loop enclosure constraint. But for the rough terrain, landmarks are few. So to work with the landmark-based constraints is difficult. So we choose our tab because it worked on the odometry constraints and the loop enclosure constraint. What I meant by the loop enclosure constraint is that when a robot moves in an environment, and goes to a new environment, so it always try to uh, correlate whether it reaches that environment before or not, and using that it try to build a map. So it has the two frameworks, local loop enclosure and the global loop enclosure. So basically, in local loop enclosure, you don't have a memory storage part, but in global loop enclosure, you have a memory storage part. So whenever a robot moves to a new location, it compared it with the previously viewed location, and if it is not matched, then it is stored it in his memory. And RTAB uses the global loop enclosure technique. And you can see in this loop enclosure why this loop enclosure is important. You can see in the two images, if loop enclosure is disabled, it keep continuing mapping the same area twice and thrice. You can see this gate. When the loop enclosure is disabled, it mapped the gate thrice. But when the loop enclosure enabled, it recalled that it previously detected that environment, so it mapped that only once. So how this RTAB basically works, in the front end part of this, it takes the odometry constraints and the loop enclosure constraints and store all these datas, and then after the back end, it optimizes and assembles all that data to build the occupancy grid of that graph data. So we not only implemented these RTAB and Octomap, we also do the point cloud data analysis from the 3D LiDAR in the MATLAB, and you can see that. So now these are the 3D LiDAR simulations and the depth camera simulations.
Okay, so we tested our results on two bots, but we did see that there was some scope of improvement, and we planned on implementing them in our future works. So one of the major issues we faced was the mapping of the depth of the rough terrain. The simulations we did in there's a world in our GitHub called Inspection World. They were pretty promising, but the mapping we was still not happy with the mapping. So in the future works, we would like to enhance our mapping techniques by using triangular mesh maps, and we also plan on changing the pure pursuit controller into something like a model predictive controller, as I'm aware that there is a model predictive controller toolbox in MATLAB. There are also we also would like to go through dynamic obstacle avoidance in the bot, because I think it will help in some real time usage. And we would also like to explore more toolboxes in MATLAB, like parallel computing and the LiDAR toolbox. That's it from my side. Thank you. Is there any question?
So you can ask any questions you have.
Sure. Yeah, thanks. Again, a very, very nice presentation, and I can see you have done a lot of things and a lot of tasks, including mapping, navigation, path planning, and also the co-simulation between Gazebo and MATLAB. That is something that is also very, very nice. So, I mean, one question to you: what was the most challenging part in this particular project for you? Uh, which of the tasks you find you found most challenging?
So, as we started the project, we felt that the co-simulation part was going to be the most difficult, but using the documentation that we got for the turtlebot, that turned out to be pretty simple. But once we switched to Curiosity Mars rover, we realized that the sensor data that we are getting from the Curiosity Mars rover was not exactly correct. There were certain issues in that, and because of that, the mapping of the environment wasn't perfect, which is that cost us a lot of time. The entire phase that we used on Curiosity Mars rover for us was one of the hardest parts. But after that, after once we settled on the Jackal bot, things pretty much fell into place. We also faced issues in AMCL localization because we use the documentation, but we had to spend a lot of time to tweak and configure the exact values that we had to give in the AMCL localization, like the number of iterations, the points that were deployed. It took a while to get the exactly localized map that we can see here. That was one of the
Yeah.
most challenging parts.
Okay. Okay. Nice. Uh, yeah. So, the Curiosity rover, what was the challenge you said? The
Sir,
sensor data that you
yes.
yeah.
So the Curiosity's Mars rover has certain cameras which are there, but
Mhm.
they were not configured correctly. They were not calibrated correctly. So whenever we were trying to co-simulate with MATLAB and get the data from MATLAB, we were not
Mhm.
getting the correct data. Even mapping was difficult. We initially we thought that the issue was with the co-simulation of MATLAB and ROS, but when we tried it just using ROS, like mapping just using ROS, using a launch file that we found for gmapping,
Mhm.
even then we were unable to get the mapping environment properly. So I'm assuming that there was some certain issues with the sensor. I think my teammate would like to add on
I
to
mean,
this.
In
right, sure.
Curiosity rover, we added a lot of things like RTabros, the Octomap, because for visualizing the sensor, there's no packages allotted in that website which we chosen to take the Curiosity rover. So we implemented the new technologies like Octomap and the RTab, because using that we are able to configure our sensors. And in Jekyll also, first we tried that things with the Jekyll, and in Jekyll it works very well. So we implemented all that thing in the Curiosity rover as well.
Okay. All right. Yeah. Maybe there could be the issue with the model itself, as someone said, right? Modeling the sensor and the calibration bit, so that be
Yes, sir, we feel
difficult.
so.
All right. And so you also mentioned particularly this Octo map kind of algorithms. You said it primarily works good on ROS 2, right? So did you happen to use ROS bridge to connect ROS 1 and ROS 2 as
N-
well?
No, basically we read the documentation of the Octomap and we have changed the dependencies which are for the ROS2, and then we installed all that package and changed the dependencies so it worked with the ROS1.
Okay. All right. So you, without using ROS bridge, you purely
No,
converted it to.
yeah, yeah,
Okay. Okay, nice. Yeah, that's good to know. And yeah, initially you mentioned various algorithms like K star, RRT, RRT star, and so on. So, which algorithm do you think works best for this particular problem? I mean, just autonomous navigation in the rough terrain. Which algorithm out of all these works best, and how do you compare those algorithms?
So we compared on the basis of the path length and complexity. So in real life, if we want to implement some vehicle which works in rough terrain, so I would say hybrid A star would work the best. But in our simulation and whatever we implemented in MATLAB, I found out like RRT star was the best because the results were quick and it was it pretty much gave the perfect path, and we need not it used less computation, and we didn't have to tweak the like iterations, maximum iterations, and the distance so much.
Okay, fine. So yeah, I mean, two criteria you mentioned is one of them is path length and other you mentioned like complexity. So how do you measure complexity? Is it just the computational time or something else?
Sir, I would say branching, on the basis of branching the complexity. Also, if the grids are means if the grids are finite, but when the area of map increases, there are more grids and discretization is huge. So for that mapping, like the algorithm might be slower.
Right. Okay. Yeah, that's fair enough. And that probably you can also learn more about this because so now, particularly if it is just autonomous navigation around a rough terrain without obstacle, probably one algorithm might work better than other. But
It is
if you
with
add
obstacles,
obstacles,
sir.
yeah, it is with obstacles, right? But yeah, I mean, depending on what kind of obstacles are there, where those are placed, and also if the obstacles are dynamic obstacles, then as well, I mean, some other algorithm might work best for that particular case, right? So I mean, it's always sort of good to understand all these algorithms better and in depth, like which algorithm works best in which case and so on. Uh, I mean, not for this project, but if you're planning to extend this to something else, then I think that knowledge would be quite useful for you. So, I mean, that's just one input from my end.
Sir, for now, we did everything like on global all the planners that we used are global path planners. Like we already loaded the occupancy map in there. We already made the map
Right.
using SLAM, and that's how we like converted that PGM file into occupancy map and then use that one. So for now, it
Sure.
is just go global path planners.
So
Sure.
can you
Fine.
give a
Yeah.
suggestion of
That's
this our project is well enough so that we can submit it to the MathWorks? Because all
yes.
the
I mean, it's yeah. Yeah. Go ahead.
okay, because all the documentations which we read in that GitHub repo, we did all that things. We implemented various path planning algorithms. We like differentiated them. Uh, like all the things which are mentioned in that, including the 3D mapping. We did all those things. So is it good to submit
Right.
it right now?
Yeah, you can submit it, but if you plan to work on this project a little bit more, then you can, the thing that you mentioned about MPC, implementing MPC, right, model predicted control, if you plan to do that, maybe in next 1 month or so, and if you are able to complete that, then that will also add much more value to the to your submission, right? Because there is, I guess there is already one submission from someone from some other university, right?
Yes.
So you will probably have to see like how your solution is different from their solution. That's one thing. And if you're able to do MPC, then that's great. But otherwise, I mean, in any case, even if you submit it right now, that's still good enough submission, I would say. Right. So yeah, I mean, if you're okay, if you're happy with your work, you can immediately go ahead and submit it as well. That should be perfectly fine.
Okay. Thank you
You
so
know
much.
the steps for submission, right?
Yes, sir.
Yeah, sure. Okay, thanks.
Okay, next group.
Good evening, everyone. We are the team number 4 under the domain of intelligent vehicle and robotics. We are all from BTech second year from mechanical. I am Nilesh. Today we are going to present to you our project of working of quadruped pet robot, which will be demonstrating using RViz and gazebo setup. We refer to the some repository like CHEMS and Macadamic also. These are some these are some pictures of our robot. These are some pictures of robot in the gazebo and RV setup. And there is also one robotic arm which will be shown in upcoming slides.
So hello, I'm Kwab Gupta. So this this video demonstrates how the robot is capable of self-planning path when provided and reach its final position, which is given in the R-way successfully and by avoiding all the obstacles which is present between them. We use a SLAM simulation localization and mapping, which helps in building a maps and localize the robot in the map. So this is another gazebo world we made, and the robot is moving around it. But this time the body of the robot is transparent, and only the skeleton and the joints is showing. As you can see, it is moving. So now this is our robot army. First we launched our gazebo world, and after that we use ChifChamp repository and download all the configurations of different robots present in them. Then after that we swam the robots in the gazebo world, and by changing some code, we import it in on the different positions of our gazebo world. The name of these bots are Mini Buffer, Cheetah, Animal B, Animal C, etc.
Now I will like to tell you about the robotic arm. So in robotic arm, robotic arm, we imported from Macadamic repository and implemented it from Move It software. So, like from academic repository, we git cloned it. Then we add joints to it like child link, parent link, and joint name link like world. And after that, we get on the Move It software. We ROS launched it, and then and that on going on path planning. Uh, After going on path planning, we added 6 joints to it. Then you can see the video that we were doing like. Not- So you can see that on changing the goalpost and then clicking on plan execute, so the robot was also working on gazebo and RVIZ. So and the many things we faced in this like we like we learned many commands in Linux like mkdir, git clone, and sudo apt, and many more things, and many things different. Also, we learned on Linux and ROS like Like we have to do setup bash outside our workspace, and like cat can make, we used to do outside the src folder, and many more things. Thank you.
We also made the CAD model of the robot on Fusion 360, and this is the video of the same. Uh, and we created different gazebo worlds and ran the robot simulation in it. And some of the applications of the of a self-planning robot are firstly home assistance. Robots can be used in assisting the people with disabilities and elderly people with some of their household chores. And secondly, it is warehouse automation. Robots can optimize order picking and warehouse management and goods transportation inside the warehouse. Uh, and our future plans is to collaborate with the IVDC club and make IVDC and the robotics club and make it in an offline mode. Thank you.
Thanks, team. That's it, right? The presentation.
Yes, sir.
Sure, fine. Yeah, I mean, this is good that you were able to work with Gazebo. You're able to develop your own model of the quadruped robot as well as manipulator and so on. So, few questions. You developed your own quadruped robot model in Fusion 360, you said, right? So, were you able to get that model into Gazebo environment as well, or you just use the pre-built models for quadruped robots in Gazebo?
Sir, like first we implemented it from repositories and move it software, and then we
Mhm.
started to do CAD model into it. But uh, we will do it in future, like implementing the CAD model into it.
Yeah, sure. Because since you have already created your own CAD model, uh, you can probably take that and see whether that can be worked in Gazebo or not, and so on. Otherwise, you can also see that CAD model probably. So, did you use MATLAB Simulink for any of the part at all, or not in this project yet?
So we will be using it afterwards, like when we will be adding the sensors into it and then calculating the results we are getting from sensor. Then at that time we will be using MATLAB and Simulink into it.
Okay, right. Because if you plan to use MATLAB Simulink at some point, right, there is something called a SimScape and SimScape Multibody, which is again the physical modeling platform. So if you have developed your own solid model already, you can directly import that model into SimScape Multibody as well, using step files or STL files and so on. You can get that into SimScape multibody, and that is where you can then add your controllers to each of the joints. Say, for example, right now you have your quadruped robot model with you, and that has multiple joints, right? So at each joint, there would be one actuator sitting in there, like DC motor or something like that, and which will move the legs of that particular robot. So you will be able to add controllers for each of these motor into that particular environment, which will then help you to take your project further and maybe move the robot as per your wish. And if you want your robot to climb the stairs or I mean, go down the stairs and so on. So all these things, you should be able to do that using that particular thing. And if you look at one of the excellence in innovation problem statement related to the same quadruped robot, uh, that also describes, or that has another problem statement is like you can combine the quadruped robot along with the manipulator to perform certain tasks. So right now you have quadruped robot with you, which can navigate and which can go from one place to another and so on. But if it really wants to do some useful task, you can have your manipulator model that you have also created. You can try putting that manipulator model on top of your quadruped robot so that that manipulator can do some useful task like pick and place and bringing some object or navigating some object from one place to another and so on, right? So that those can be considered as few of the next steps for you, and you can go through the excellence in innovation page that has certain resources associated with that as well, right? So yeah, but since you got started with this particular thing and already developed some models work with Gazebo environment, so that's something I'm sure you might have learned a lot of new things while working on this, right?
Yes, sir. Sir, also like you told like rhyming on stairs, sir, we will be doing like that. Like CAD model we have made, and then at the joints we will be adding servo motors, connecting it to Arduino,
Right,
and like making the joints angle that at what angle it has to climb. We will be measuring the thickness of the stairs. And also
right,
like
right,
in robotic arm we will be adding like fingers to it and adding servo motors or mg9 and 5 motors to it, and then we can give it commands like at how much angle it has to rotate to hold a can or some object placed above it, and then drop it. Yes, sir.
right. Sure. Yeah, that's good to know. But even before going to hardware, like even before going to Arduino board or some other hardware, you can try doing that in the simulation environment as well. Of
Yes,
course,
sir.
you can parallelly start working on the hardware, uh, but hardware will work at some point of time, but it will not be optimized. To get optimized results, you can also parallelly try that in your simulations as well, so that you can fine tune the parameters to get better results.
Okay,
Right?
sir.
Sure. Thank you.
Thank you, sir.
Thank you. I'll call upon the last group for the day.
Okay. Good evening, everyone. So I am Rakshit Jangir, and he is Pulkit Gupta. And the problem statement that we worked upon was path planning for autonomous race cars. So, as we all might be aware of that, there is a very famous saying in the racing domain that in order to finish first, we must first finish. So, with that quote, I think we should start the presentation. So, our basic goal was to first generate an optimized trajectory and then develop a vehicle driver model in Civilink, which will follow that trajectory. And the aim was to minimize the lap time. Okay. So first of all, we would like to start with introduction to path planning. So I guess that is, as the name suggests, path planning is nothing but creating an optimized path which the vehicle can follow in order to minimize lap time. And as well, if there are obstacles in the path, then we can deploy obstacle avoidance algorithms, which will avoid those obstacles and go through there. And yeah, why is path planning important? That is because in the whole autonomous racing domain, the first step, I guess, is path planning. So one of the part is offline trajectory optimization, and another is online trajectory optimization. So in many of the competitions, you are not initially given access to the racetrack. So in that particular case, you will have to deploy the online trajectory optimization method, but in many of them you are already aware of the track, and or in other case you can probably use slam and then get the map, and once you have the map you can deploy your algorithm which will generate a trajectory, and the vehicle can follow it. So yeah, basically there are two parts of it as I just mentioned. First is trajectory optimization, and another is vehicle driver model. So first, Pulkit will talk about trajectory optimization.
So in trajectory optimization, I would like to say that we took the tracks from GitHub repository. Now we got the track. So first we needed to refine the tracks. Like there was very less segments for the tracks in the GitHub repository. So we increased the number of segments and we plotted the track using the interpolation function. Interpolation function helped us to increase the number of segments, which would give us more proper results, and at the same time it gives us smoother curves so that we could plot the track and had our constraints. Then we made the objective function helped us to uh, means it governed our trajectory optimization so that we could make the lap time as small as possible. And we solved the objective function using the quadproc function, which is in the optimization toolbox of MATLAB. So in the quadproc function uses a quadratic equation which has constraints so that it could optimize it. So in the quadproc function, the constraints are also kept in mind, and it follows a linear form set of constraints. So the quadproc function matched our requirements. That is why we use that. Now we have two types of algorithms. Generally we follow two types of algorithms for path planning in the racetracks. One is the shortest trajectory and another is minimum curvature trajectory. In the shortest path trajectory, the distance which will the trajectory give will be as small as possible, so that the distance covered by the car is less. So indirectly it may seem us that the time required to cover the whole track is very small, but we know that the F1 tracks have many sharp curves continuously. So what happens in the shortest path trajectory is that it follows the shortest possible path, and we know that while turning at short path at short curvatures or at maximum curvatures, we cannot move at higher speeds. That is why the drawback of shortest path trajectory is that at the curves. And similarly, in the minimum curvature trajectory helps us to increase our speed at the curves, but at the same time it increases our distance. So now we know that both the trajectories are not good. Means there are some pros and cons for both. So the proper optimized trajectory will be a combination of these two. Like at the curves, the minimum curvature trajectory will govern to take the minimum curvature path so that we could cover it at higher speeds, and at the same time at straight lines, or like when we could go nearly straight, so we can take the shortest curve trajectory, so that uh, the distance covered is less and directly the time consumed is less. So the final optimized trajectory is a linear combination of these two trajectories. Now I would like to give the mic to Rakshit. And yes, another thing, in the these are the figures for the Austin track. We enlarged them, so at in the leftmost figure we can see that the uh, means red line shows us the optimized trajectory, so we can clearly see that the curve is taking the maximum curvature, and it also follows the internal line which will give us the shortest distance. And the centermost figure gives us the minimum curvature trajectory. We can clearly see at the curves that that the optimized trajectory is further from the maximum possible curvature. And in the optimized trajectory, it is the mixture of two. By we added some weights, and we got the optimized trajectory. Then this is for Silverstone. Now I would like to give mic to Rakshit.
Okay. So now once we have the trajectory, our next task is to develop a vehicle driver model. So the first part is developing a vehicle model. So basically there are three major types of vehicle model that we could have used. So the first one is the most simplistic vehicle model, and that is the point mass model. So it does nothing but it is a very poor approximation of all the forces that are acting on the vehicle. So what we actually do in point mass model is consider the whole vehicle as a single point mass and then compute the forces on it. So it just takes into account the forces, and no dimensions of the car are actually used. So, and on the other hand, we have a dual track model. So dual track model is the complete opposite of the point mass model. So the dual track model is basically consider all the four wheels of the car and the rear and front axles, and with the help of various tire models and all the traction forces, or rather all the forces that are acting, we find out forces on each of the tires and then find the resulting forces that are acting on the car. And the model which we used was the bicycle model. So the approximation or the condition for using a bicycle model is that what we do is we instead of taking two tires in the front axle, we just take one of them. So we combine two of the tires into one. So basically, uh, yeah, here is the picture of a bicycle model. And the reason we chose bicycle model was that the dual track model uses the Ackermann steering constraint, but the thing is at higher speeds, the Ackermann steering constraint is not valid. So the slip is not accounted many a times in the dual track model. So that was the reason we use this bicycle model. Okay, so the first part, once we have the model, the first part is to design the vehicle dynamics. So there are many parts of it. So the first part is the most basic one, that is rolling friction. So it is nothing but it takes into account the friction that is acting on the car due to the relative velocity between the car and the racetrack. And another one is tire slip angle. So the slip angle is basically the angle between the direction in which the wheel is actually pointing and uh, and the direction in which it is actually moving. So that is the slip angle. It is basically used in calculating the lateral and longitudinal forces as well using the tire model, which we'll talk about later. And the third component of vehicle dynamics is the aerodynamic drag. So it is nothing but the force that is, or basically resistance that is applied to the motion of the vehicle due to the relative velocity between the wind and the vehicle. So for autonomous racing, or rather for racing cars, it is actually a very dominant factor. And at higher speed, it gains its importance because aerodynamic drag is proportional to the square of velocity. And the last component is the traction force, which is obviously the force due to the motor and the engine that helps the vehicle to move forward. Okay. Yeah. So now talking about the tire models. So there are various tire models. So the most basic is a linear tire model. So it is a very it is like preliminary one. So what it does is basically considers the linear relationship between the slip and the lateral force. So it is we can say it is an approximation of the Pajika magic formula model as well. So it is only valid for lower slip ratios, but at higher slip ratios it fails miserably. So we avoid using it often. Another model is the Dug-off tire model. So it is a mathematical model, and so the main basis of it is the slip angle. So it takes the slip angle as the basis and computes the lateral forces. And the third one is the Pajiga magic formula model. It is one of the most advanced models. It is very complex and comprehensive. The thing is, it has various parameters, so it is quite computationally expensive at times. So, but yeah, we use the Pajiga magic formula model because at higher speed it gives much accurate results. Okay, so now once we have the vehicle model ready, our next task is to design the driver model. So there are two things that driver controls. First one is the steering control, and another is the traction control. Uh, okay, yeah, throttle control. Sorry. So the talking about the first one, that is steering control. There are three basic ways you can three basic algorithms for steering control. The first one is the pure pursuit controller, which we eventually used. The reason we used it because it is quite simple and at the same time it is quite robust. So that is the thing, and it uses a look ahead distance, and depending upon the look ahead distance, it calculates the next goal point, and depending upon that, it calculates the delta, that is the steering angle. Second one is Stanley controller. It is quite similar to pure pursuit controller, but there are various differences in it. And the third one is model predict control. That is quite an advanced steering control algorithm. because it uses a cost function and then try to optimize it. So, and it is also computationally expensive, so we didn't use it. Yeah, so the last thing about it is the speed control. The first part of speed control is to generate a reference velocity or a velocity profile. So that is done in accordance to the friction circle diagram. So we keep in mind curvatures at various points, and keeping into the mind the curvatures at all the points, we calculate the reference velocity that the vehicle must have, and we also impart some constraints on it. And then once we have the reference velocity, our task is to minimize the error between the reference velocity and the actual velocity of the car. So for that, uh, we can use PID control. So we used an inbuilt block for this. So yeah, the PID control is very basic control, and as well it is used at many places. So that was the reason we used it. Model predictive control is again a very advanced one, so we avoided using it at all. Yeah, so now once we have all of it ready, we need some power for the vehicle. So that power is given by the powertrain. So for the powertrain model, we use the constant torque, constant power model. So basically, at low speeds and higher loads, the constant torque region is used. So basically, what happens is in constant torque for a variety of speed ranges, the torque remains constant. So that is quite advantageous. And when the velocity is quite higher and the loads are less, we use the constant power region comes into the picture, and what it does, it keeps the power constant and varies the torque in accordance with the rotational speeds. Yeah, then we used MATLAB Simulink for this. So the first part, that is the trajectory optimization, was done in MATLAB. We use quad proc function, as Pulkit just mentioned. And the second part, that is developing a vehicle driver model, that was done completely on Simulink. So yeah, and then we tested. And there are some real world applications. So one of the very famous autonomous racing competitions is F110th racing competition. So that uses various path planning algorithms and stuff. And another one that is very famous is Indy Autonomous Challenge, which is organized annually by Cisco. So these are some of the very famous autonomous racing challenges. Yeah, and coming to conclusion, future improvements. The thing was that we faced some errors at the end in Simulink file. So that was, we plan to fix those errors as soon as possible. We tried it multiple times. We tried to minimize the step size and the solver for the uh, model, but it didn't work eventually. So that was the thing. We tried to resolve those errors, and then and once those errors are resolved, we plan to implement the obstacle avoidance algorithm, and then overtaking, and finally hardware implementation if time permits and stuff. So yeah, that is it from our side. Thank you.
Thanks, thanks both of you for nice presentation. Uh, and mostly, I mean, I can see you have studied a lot of uh, algorithms and or a lot of models and various things like tire models, various kinds of tire models, various kinds of controller models, and so on. Also, uh, shortest path as well as minimum curvature models, algorithms, and you did the combination of that, right? So, I mean, you mentioned that you did linear combination of shortest path and minimum curvature algorithm. What do you exactly mean by that? So, how did your objective function change in that particular case?
Sir, like we means for the tracks we first generated both the trajectories, shortest path and the minimum curvature, and then we took some weights, like we assigned some weight to shortest path, and then we reduced that weight, means like if the total amount of weight is 1, so we gave 0.02 to shortest path and the rest to the minimum curvature trajectory for all the segments. So at the
Right.
end we had a mixture of, means it was a mixture of both the trajectories.
So that weights you added into your optimization problem, or
No, sir.
what's the optimization problem? Okay,
uh,
so how
like
was that?
like we first generated the matrices for the shortest path and the minimum curvature, and then we added the weights in the matrices, and then we means put the matrices in the quadproc function, which gave us the optimized path.
Okay, okay, all right, sure. And okay, so you yeah, in terms of controllers I mean final path controllers, you said you used pure pursuit algorithms and uh, not the Stanley and MPC and so on. But did you find any limitation in using pure pursuit algorithm as such?
Sir, as such, I guess we did not face a lot of limitations because the thing is, the vehicle is a race car. So what we need to do is we are going at very high speeds. So at very high speeds, what we need is uh, a pretty accurate waypoint. So at higher speeds, it works quite well. But as such, I guess we did not face much difficulty. So the thing was that the error part was also a major hindrance to it. So we couldn't see all of the results that we planned to see.
So what was the error? Can you do you can you just maybe briefly explain that?
Yes, sir. Initially, uh, there was some error in our pure pursuit code. So that yeah, we had written our own code for pure pursuit controller, but then eventually I guess there was some issue that they were saying that goal point is not defined at all the points. Then we tried solving it, but then we went through all of the code thoroughly, but it turned out that we had taken into account all the possible cases while turning and while finding the goal point. But then since it was not running, we used a much simpler code that we've just found out the just took the next waypoint as our goal point, and just took the look ahead distance as a function of velocity. Yeah, so we took a much basic model, and then yeah, so that was rectified. The pure pursuit part was rectified, and then once all of it was complete, all the model was prepared, we started running it. So there was some error in the algebraic loops. So initially
Okay,
there were error in algebraic loops, and then I tried inserting unit delay blocks in it. Many of them were rectified, but there was an error in I guess an integrator block, and it said that the uh, output that I'm getting, that the compiler is getting at some time, is either infinity or not a number. So that we was not able to rectify.
okay, okay, sure. Yeah, I mean, if you want to work on that and get that error resolved, you can either write to me or you can write to the email that is support@mathworks.in. You'll someone from Mathworks will reach out to you on that. So you can write an email to that particular email ID as well, right?
Sure, sir.
That is one thing. Yeah, I was specifically asking about that because MPC controller, right? You mentioned it's little advanced and might not be suitable for this application. But if you're planning to take or extend your work, and you mentioned in your future work like you want to overtake another vehicle and so on. So, for example, if you're overtaking another vehicle and there is third vehicle in front of the next vehicle, then in that case, probably pure pursuit algorithm might not work best. So that is where MPC algorithms, MPC controllers become usually they are more handy in that particular situations where you have not only the objective function to satisfy, but you also have multiple constraints around that objective function. So that is where MPC controller actually plays a very important role, and that has more sort of advantages over classical PID controllers or pure pursuit algorithms and so on. So I mean, not necessarily for this work, but if you plan to extend it for actual race car autonomous vehicles racing environment, that is something that you can I mean, consider of considering using that. And one last thing is, so since yeah, you have developed this model, and it's I mean you have developed this algorithms, that's working fine. I really like the linear combination part of the shortest path and minimum curvature. uh, when you really want to simulate that onto real uh, I mean sort of real environments, you can also consider developing the scenario for your race tracks. uh, so there are few scenario designer tools available, also in MATLAB and few others as well. In MATLAB Simulink, there is scenario designer application using which you can create scenarios. Also, there is another tool called Roadrunner. So using Roadrunner, you can actually create real life scenario for roads along with the obstacles or signals and trees around the road and so on. So that, using that kind of platform, you can also create your own scenario and then test out these algorithms onto the vehicle which will run into that particular roadrunner. Roadrunner and MATLAB Simulink can also co-simulation can happen between Roadrunner and MATLAB Simulink, and you have access to Roadrunner as well as a part of your IIT Bombay, IIT Indore uh, licenses. So if you wish, you can also try doing that. And if you do that, then probably you can also submit your solution to the MathWorks Excellence in Innovation problem statement that is there, because that was one of the steps that was mentioned there. So if you do that and if you uh, get good results, you can also consider submitting your solution to this particular page so that you will also probably get recognized by MathWorks, right? Sure. Yeah,
Yes,
those
yes.
were my inputs. But yeah, overall, good work. Thank you.
Thank you so much for your input, sir.
Sir, I would like to add one point. Like the in the question you asked for the optimized trajectory. So we are also planning to work on online trajectory. Like we have the track segments, and each segment will have its own weight. Because of some
Okay.
errors, we were not able to do that, which Rakshit just mentioned. So the confusion is like we are taking weight for every segment, so it would not give us the perfect optimized trajectory. The best perfect optimized trajectory will be given in the online optimized problem. So each segment will have its own weight, so it would be better. Means we think that it will the car will take more less time to means lesser time to cover the track.
Right. Yeah. Probably. Yeah. You'll have to check that out and compare that with your earlier algorithms as well. Yeah.
Yes, sir.
But yeah, I mean, this is nice way to think about solving that problem. Yeah. All the best for that work. Thank
Okay,
you.
so thank you. We were very happy, especially with the questions that were asked to the teams. Right. So I would really like to thank you for sparing your time and coming here. I know the event has gone a bit longer than
Sure.
what we
Yeah.
had hoped for, but yeah. So I'll send you the reports and slides, and you can send your response in a few days.
Sure. Sure. Fine. Yeah.
Okay.
That will be helpful.
Yes, sir. And
Please send the
if you have
reports
any
as well as
feedback,
the
if you have any
presentation.
inputs, you can kind of just say it right now if you'd like to.
No, I mean all the four groups which presented here, I mean, who presented here, uh, they have done a quite nice work. I liked all the projects, especially. I mean, I'm not expert in all of these, but at least I got to know like in which ways you can work on a particular problem statements. You have worked on various tools, not only MATLAB Simulink. I'm sure you got opportunity to explore. Some of you work with Gazebo, some of you work with open source softwares, learn different architectures from CNN, YOLO, and few others. So I mean, I'm sure this would have been a nice experience for you to work on these projects for last couple of months, I guess. And I'm sure you'll take these learnings ahead and use it for your final year projects as well, which probably you will do in your final year. And uh, also think about this opportunity. Like you can probably extend this work convert it into a research problem, a research project, and also publish it in terms of conference paper or journal paper. You can either seek help from us as well from MathWorks, but also you can seek help from your professors in your departments, mechanical or electrical, whichever department you are working in, and of course your seniors. So yeah, that's all I
Absolutely,
had to
sir.
say.
Yeah. Thank you.
Thank
I'll
you. Thanks a
end the
lot.
meet today. Yeah. Thank you.
Sure. Thanks. Bye.
Bye.